Hello everyone, welcome to Mayur Programming Club. Today we will be solving another daily lead code problem, and the problem's name is modify graph edge weights. Okay, so you will be given an undirected connected graph that will be having n nodes labeled from 0 to n minus 1, and an integer array edges will be given to you, where each entry in this edges array will be of this particular form, where the first two entries in this array will be the nodes between which the edge is existing, and the third entry will be the weight of that particular edge between these two nodes a and b. Okay, so some edges also have a weight of -1. Okay, and while rest of the edges have a weight of greater than 0, or you can say positive weight. Okay, so your task is to modify all the edges with a weight of -1. So by assigning them a positive integer value, so you should be replacing their -1 weight with a positive integer value, and those values will should be from the range 1 to 2 into 10 raised to power 9, both inclusive. Okay, and so that the shortest distance between a particular source node and a destination node that will be given to you in the input also, so becomes equal to an integer target, which will also be given to you as input. Okay, so if there are multiple such modifications that can make the shortest distance between the source node and the destination node equal to the target, then any of them will be considered as a correct answer. Okay, and you have to return an array containing all the edges, or even the unmodified edges, the edges which were already having positive weights, in any order whatever you may like. It is, if it is possible, to make the shortest distance from the given source node to the destination node equal to the target. And if it is not possible to do so, provided the given rules or the instructions that have been provided in this problem statement so far, then you should be returning an empty array showing that it is impossible to do so. And there is a note further down the problem that you are not allowed to modify the weights of the positive edges. So you are only allowed to modify the weight of the -1 containing edges, and only within only with the values within this range 1 to 2 into 10 raised to power 9, both inclusive. Okay, so this is the problem statement. Now before thinking of an approach, let's have a quick look at the constraints also. So you should be definitely knowing about the constraints, only then you would be able to understand that what kind of algorithm will be suitable uh, to solve this particular one, so that our solution becomes accepted and it does not give a time limit exceeded error. Okay, so otherwise you will just end up wasting your time and implementing a solution that might be taking a longer time that is allowed. Okay, so according to the constraints, the number of nodes will be of order 10 is 100, and the edges array length will be of order n square. Okay, and edges, each entry in the edges array, as we have already seen, will be of size 3 fixed, and the entries in the edges array, those a and b values of the nodes that in between which a edge is existing, will be valid integer values ranging from 0 to n minus 1, as it's already mentioned in the problem statement that n nodes from 0 to n minus 1. Okay, so this is what it is saying. And then only two types of weights, either a negative weight of -1 or a positive weight in this particular range. Okay, and no self loops. So node will not be connected to itself with an edge. Okay, and source and destination will be valid nodes. Okay, and source will never be equal to the destination, and the target value is ranging between 1 to 10 raised to power 9, both inclusive. And it is further stated again that no self loops or repeated edges. Okay, so these are the constraints. So let's try to think of an approach. So before thinking of an approach, we need to make some observations, and those observations are these. Just first of all, the very first thing that came to my mind is, what if I remove all the -1 containing edges and try to find out the shortest distance from the source to destination? Okay, from source to destination. And let's say there exists a path even without those -1 weighted edges, and if there exists a path and it gives me some shortest distance values. Okay, I will apply some technique. Let's say X technique will give me uh, the shortest distance. Okay, for that, for right, discuss for this discussion, let's consider it as a kind of a black box. We do not know what it is and how it works. Just it simply gives us the shortest distance. Okay, it gives us some value of the shortest distance. Whether the path exists or not, that depends on the value of the shortest distance. So let's say we get some shortest distance value. Okay, so if we get some shortest distance value, and if the shortest distance value is equal to the target value, then we would be really happy, saying that okay, we need not to do anything now. We have to just make sure that those -1 weighted edges, when we will be replacing them with positive integer values, so we should be replacing them with such a value that they would not be able to contribute to the shortest distance path. Okay, between the source and destination. So in order to do so, what we would be doing here is, we would be giving them this value. Okay, but this is a very high value, and the target value, as you can see, was up to only 10 raised to power 9. So if you give twice of that, then obviously it will never be the shortest distance. Okay, if the shortest distance is already equal to the target value. Okay, so assign the highest possible value to -1 edges so that they can never contribute to the shortest path. This is one case. Another case that can be there is, if the shortest distance that this technique gave us or told us between source and destination, without, I repeat, without -1 edges, is less than the target, then what this means? See, if this kind of situation happens, then you would never be able to make the shortest distance equal to the target. And why is it so? You would say that okay, we would consider the -1 edges also, and then somehow we would be able to increase this to the target. Okay, but it will not happen. Why so? Because if addition of -1 edges will do either of two things. It will either even further decrease the shortest distance by providing a more optimal path. Okay, more optimal path it can give. You can give minimum value. So the minimum possible value that you can give to such edges is 1. If let's say it gives you more optimal path. Okay, and let's say other way around, you are already having the optimal path, and even after addition of those -1 edges, uh, your path shortest distance will still be the same. Okay, so in that particular case, you will never be able to no increase your shortest distance to the target value. Okay, so in this particular case, you will be returning an empty array. Okay, shortest distance either will remain same or even decrease further. Okay, will never be increasing. Okay, so this is one case in which you will be returning an empty edges array, showing that it is not possible to achieve what the problem statement asks us to do. So we are returning an empty edges array. The third case is that if the shortest distance that the technique told us between the uh, source and the destination, providing that we are not taking into consideration the -1 weighted edges, is already greater than the target. Okay, so in that case what we will be doing? So see, if it is greater than the target, then we will be a little greedy or wise here. We will be replacing -1 weighted edges with the minimum possible value, because the shortest distance is already greater, so we must find a shorter path. So the least possible value was 1, so we can give this particular value. What we will be doing here is, we will not add all the edges in one go. We will try to add these -1 edges by replacing them with one value first, one by one, and after each addition you will try to find out the shortest distance again. You will ask that technique, okay, give us the shortest distance after we added this particular edge with value 1. Okay, so if the shortest distance is still larger, then you will keep repeating uh, this particular process of adding one weighted edges. Okay, but if there is a situation that the shortest distance either becomes less than or equal to the target after addition of one such edge, what is that edge? -1 edge replaced by one weighted edge. Okay, one weight edge. Okay, if that condition arises, then there can be two situations. The first situation is, let's say the shortest distance came out to be less than the target after addition of weight 1 edge. Then what you can do, since we were given freedom to give any value between 1 to 2 into 10 raised to power 9, both inclusive, we will give a higher value simply, and this value of the range that we are allowed to take values from is sufficient, so that we can increase the shortest distance to the target value. So for the current edge that we have uh, been falling short, and we will increase that edge's value, edge's weight, you can say. Okay, this is one situation. And what if the shortest distance was already equal to the target? Then no further action is needed from you. For the rest of the edges, after dealing with these two scenarios, you will be giving them maximum possible values, so that they cannot contribute to the shortest distance, which is now set equal to the target. So this is what you have to do. Now the only thing is here is that you need to find what that technique is that will be giving you the shortest distance. Okay, technique that will be giving you shortest distance. Shortest distance between source and destination. Okay, for that what I have done here is, I have used single source shortest path algorithm. Okay, single source shortest path algo, or you can say Dijkstra algorithm. We would not be covering Dijkstra algorithm in this particular video in depth. I will be explaining how things work out in Dijkstra algorithm. Basically, in nutshell, what I can tell you is, in Dijkstra algorithm, although you need not to worry about not knowing Dijkstra algorithm or not being familiar with it, a link of an article explaining Dijkstra algorithm will be provided you into the description box. and you can definitely check that out. What I can tell you is, from a single source, okay, to rest of the nodes in the graph, okay, this Dijkstra algorithms gives you the shortest distance. Okay, let's say there were nodes A, B, C, D, and E, and one of these nodes happens to be your destination node. Okay, let's say this was your destination node, and source node will be the source node that you are, you know, starting your journey from. So each node will be having this information. What is my distance from the single source, this source? Okay, A will be knowing that what is its distance from that source. B will be knowing that also. So you will go to B in a way and say, hey, what is your distance from source? And it will give you that distance. Basically, this is what this algorithm will help you to do. Okay, and these distances from the single source will be stored in a array like structure, uh, indexed from 0 to n minus 1, each representing the edges or the vertices, sorry. Okay, and this is what this algorithm will help you to do. And if you are more interested in, or you are not familiar with it, prior to this particular problem, then please head over to this link and read that article, and you will be knowing what the basic implementation of this algorithm is, how and when to apply it. Okay, and what are its time complexities also. So let's see the implementation, how we have used this Dijkstra algorithm, and rest of the things that we talked about, those three cases. So let's bring the code to the board. I know the video is a little bit lengthy, but this is a implementation heavy problem. Here you have to implement the Dijkstra algorithm also, and you also have to take care of those three cases. Okay, so this is the code. So we will be explaining, I will be explaining it to you line by line. So let's see how we are solving this particular problem. So first of all, this is that technique that will be we were talking about. Okay, this is basically the Dijkstra algorithm. Pardon me if some spelling is incorrect. I hope it does not really affect your understanding of the approach and the code. Okay, so first of all, the very first case, uh, to do anything at all, you will be needing a graph. Okay, we were talking about the graph right from the very start. So we will be using a map. Okay, the first entry in this pair array will be the node value. Okay, and this is let's say this is A, this is also a node value. Okay, and this is B, and there is an edge between A and B. Okay, connecting A and B, there is an edge, and the weight of this edge is something. Okay, and this weight is nothing but this particular part. Okay, so this is what, how we have structured this node neighbor map. Okay, neighbors of node in a way, connected with the help of edges. So each node will be having some neighbors or some nodes connected to it with the help of weighted edges. So firstly you are forming the graph here. Okay, and it is to be noted that we are forming the graph without -1 edges. Okay, forming graph without -1 edges. And let's remove this toolbar also. So we are skipping the -1 edges, we are not adding them to the graph right now. So we are trying to do this thing that we have, you know, finding the shortest distance from source to destination without -1 edges. Okay, this should be noted. So what you are doing here is, since the graph was a undirected graph, you can go both ways, from first node to the second node and second node to the first node. So you need to make those connections. So this is what we are doing here. Okay, this particular part. So if you are having any confusion about this particular part, then you can ask them in the comment section. Okay, it is nothing new. For the first node, if you are seeing it for the very first time, then you might not be having the list in which you will be storing its neighbor information. Then you are initializing that list for the very first time. Similar will be the case for second node. And may this is we are making bidirectional edge. Okay, from first node to second node and second node to first node, edge weight will remain same because it's the same edge only. So now we have the graph without -1 edges. Okay, and we need to find the shortest distance. This is the technique, obviously, that will be giving us this shortest destination list from source to destination distance. Okay, I have changed the terminology a little bit. Okay, so from source to destination, and you will be giving this technique the graph also. Okay, so we will be discussing the technique in a little bit after we are done with this cases. Okay, so if it is the first case, there's you know, or in the cases we discussed it, I think the second case, yeah, if it is the second case, that your shortest distance or the distance from source to destination without uh, -1 edges is coming out to be less than the target, then you will say it is not possible to solve this particular problem provided the given instructions. Okay, and you will be returning an empty edges array. Okay, so this is one scenario. Now the second scenario was either the value of the this source to destination distance that came out without my -1 edges will be either equal to the target or it can be greater. So we will have a boolean variable, and it will tell us was it equal to the target. Okay, so we will be storing it somewhere. Okay, now we will be considering these two cases together. Okay, since even if we are having this to destination distance equal to the target, then also the problem statement told us to uh, give positive values to all -1 weight edges. Okay, you cannot avoid that. So we will be doing that one by one. This time, since we have already considered the edges which were already positive, we will be only considering the edges that are -1. And if they are already positive, we will be skipping them. Okay, and see, here we are doing pretty much the same thing, but we are checking is the distance, shortest distance, is already equal to the target. If it is, then as I told you, you should be giving such a high value that these -1 edges, even after getting a positive value, should not be contributing to the shortest distance. And this infinite value I have set to be equal to 2 into 10 raised to power 9. Okay, so highest value that was possible. Okay, so this is what we are doing. Else you will go into this mode. Okay, this particular mode, if the shortest distance is greater than the target. Okay, so you will give values of 1, the least possible value, to the edge, and you will add it to the graph. You will be adding edges one by one. Okay, and this is what we were doing essentially in the above part also. Okay, and if right now your distance, uh, shortest distance, is not equal to the target, then you will do the same procedure that we discussed here. Okay, after giving one value and adding this particular edge to the graph, you will be asking the technique to give you again the fresh shortest distance, and depending upon that, two scenarios will be considered. Okay, so this is what we are doing here. So depending upon that, your source distance will either be less than or equal to the target. If it is so, then you will see how much you are falling short. If you are not falling short, then it's good, and you will say that we have reached the target. Else, you else part, you know, you have to keep adding the one value containing edges, and this thing will continue. Okay, so else is not required. That's why I don't use it, because anyways you will be repeating the procedure. Okay, so let's say you achieved the target value, and then you will be returning the modified edges. Okay, and if let's say you were not able to achieve the target value, then you will returning a empty array. So this is we are taking care of, you can say, the cases that were there. Okay, and now let's talk briefly talk about this technique. Okay, we will not be talking about this in very detail because it will make the solution video very lengthy. I would highly suggest you to, go to that link and of Dijkstra algorithm, and please have a reading of that article and try to understand it. If you are still not able to do so, then you can ask the doubts in the comment section. Okay, but anyways, let's have a quick discussion about it. Okay, so let's begin. So this technique will be getting some inputs from us, which will be the number of nodes, the start and the end node. Okay, this start node will act as a single source. Okay, single source. So what this priority queue will be giving you, it will be giving you the distance, the node which is at the least distance right now from the single source. Okay, you will be going to this queue, and in a way you can say heap, and you will be asking it what is the uh, you know source node which is at the smallest distance from the source. Initially, as we talked about, we would be having a distance from source array, and since if you are at the source, then you are at zero distance from the source, obviously. So let's say the source is the 0th value, then for source value you will be saying that it is having zero distance from itself. Okay, and the first value which will be inserted in this priority queue will be this source value, and its corresponding distance. This is the distance, and we are this uh, heap is being maintained such that it will always give you least distance value. Okay, from the source, the node with the least distance value. Okay, so this is the node value, the start node. Okay, then you will ask heap, give me the node that is at, you know currently at the smallest distance from the source. Once you take that node out, you will explore its neighbors. Okay, and you will see if we are able to update the neighbor distances from source. Okay, so if this is the condition that is holding true, let me change color here, and let me add some space here also. Okay, yeah, so in a way we will be trying to update the values of its neighbors. So these are the neighbors, you can say. Just a second. Yeah, now it should be fine. Okay, so for each node that you take out from this heap, you will be getting its value and its distance from source. Okay, and you will explore its neighbors. If it is not having any neighbor, then you will continue, okay, with getting another node from the heap. So once you are getting its neighbor values, then this edge might be having should be having some weight. Okay, and the source, let's say this node is at some x distance from the source. Okay, so if x plus the new weight, and this node will be having its corresponding entry in the distance from source array, and let's say that distance was y. Okay, if x plus new weight is less than y, then you will say that, okay, hey neighbor, we have find a shorter path for you to reach the source, so please update your uh, shortest distance from the source. So we will be doing that updation here, and that particular neighbor will be added to the heap that we were using. Okay, and this procedure will keep repeating, and once you are having nothing in the heap, you will terminate the whole process, and at the end each node will be knowing its shortest possible distance from the single source. Okay, and you will go to the end node and say what was your distance from the source, and source was nothing but this start node. This is what Dijkstra algorithm is in nutshell, or you can say uh, in a practice. Okay, so if you are still not able to understand or want to have a more in-depth understanding, I will again say that you should be going to that article's link in the description box. So this is how we will be solving this particular problem. I know it was a lengthy implementation and the video must have been very lengthy, and before ending the video, let's have a quick discussion about the time and space complexities also. So time complexity wise, see here, this particular process that we were doing might go up to order of e times. E is the number of edges. Okay, so minus one number, since you might have to check for all minus one edges before finding an edge, or you may not even find an edge, which makes your target equal to uh, source to destination distance equal to target. Okay, and since you were calling this technique again and again, order of e number of times, this technique must also be having some time complexity. Okay, so what would that be? See, for heap can have all the nodes, order of v nodes. Okay, let's say there were v nodes, v vertices or nodes. So this heap can hold up to v vertices, order of v vertices. Okay, and heap data structure, either you give it a value or take value out of it, will require order of log of v time complexity. Okay, and you will be processing each node at least once. Okay, so each node will be going through this heap at least once, so it will be taken out from the heap, you can say. So this process of taking out from the heap will be occurring at least one for each node. So overall time complexity will be number of nodes v into whatever this operation will cost us, which was log of v. Okay, this is one thing, and then you are trying to update all the neighbors of the given uh, node that you have taken out. Okay, for updating the neighbors also, if the neighbor is value is being updated, then you will be giving some value to the heap. Okay, and so, and a node can have order of e neighbors. E is the number of edges. Okay, so and this giving something to heap will cost you log of v operation time complexity, and if you add these two values, it comes out to be order of v plus e log of v. Okay, so this is the time that will this technique will cost you. Okay, and let me take a fresh slide. And if you want to combine both complexities, then time complexity comes out to be order of e into e plus v log of v. Okay, this much time complexity will be there. And space complexity wise, see here for making the map, you will be requiring e entries, number of edges, and for in the technique you are using couple of things, this priority queue and this distance from source array. Okay, so priority queue can hold up to v nodes, and distance from source array can also hold up to v nodes. So e plus v, okay, order of e plus v. So these are the complexities. So if you are still having any doubts or any queries in general, then you may ask them in the comment section. And I really hope this solution video added some value to your journey of honing your DSA skills, and keep solving more and more problems. And I will be seeing you in the next video. Thank you for watching.